All right, good evening. Welcome to lecture 22 for MT225. Lecture 21 was our exam. There were no formal notes for that. But tonight we start into our third and final phase of MT225, where we take a look at strength of materials. So we are essentially done with the applied mechanics portion of the class, and the mathematical difficulty in the class has reached its maximum. There's nothing that is any harder than what we've already done. In fact, you're likely to find the the math that's associated with what we need to do in the remaining part of the course to be relatively simple compared to what you've gotten used to doing truss analysis and frame analysis. So tonight we're gonna take a look at strength of materials, and we'll start into that tonight. I'm gonna go over a little bit of the schedule for the remainder of the course as well, so we have some idea of where we are, where we're going, and what's going to be expected in the next couple weeks. So exam 2 was returned over the weekend. I emailed that back on Saturday or Sunday. I don't remember exactly which date it was. It was one of those two. But that came back, and you should have gotten your feedback on that. I have the paper exams for those of you I see at the hangar. I will hand those back when I get a chance to. Homework 8, the bonus assignment, was also returned. So if you submitted something for that, you should have gotten something back. And our schedule, we've essentially got 4 weeks left in the course at this point. And I've kind of broken out the schedule here and our content. Tonight and Wednesday night, we're focusing on stress and strain, the concepts of stress and strain, how they relate to materials. Homework 9 will be issued on Wednesday night. So, homework 9 will be all about stress and strain and doing calculations with those. Then next week, we'll get into materials. We'll look a little bit at essentially design. We'll be trying to figure out if we're going to put a load on a particular structure, how much material are we going to need for that? What material is going to work? If we're going to load up a rivet joint, how many rivets are we going to need to handle that joint made out of what material? So we'll be doing a little bit of design. We'll work with bending and material structural design in an elementary sense. And there will be a homework on that, homework 10. Homework 10 is essentially a bonus assignment since it'll be due on the night that we'll be having our exam on strength of materials. So first week of May, May 3rd and May 5th, we'll be doing some strength of materials review. We'll put everything together into some practice problems, and then we've got an exam. So exam 3, and exam 3 is a good chance if you didn't do so well on exam 1, and everyone did pretty well on exam 2. I was fairly happy with the scores on exam 2. So most everyone did pretty well on exam 2. So exam 3 is a chance to really make sure you improve your score from exam 1 if things didn't go so well for you there. And it's on some pretty straightforward stuff. So I'd usually expect relatively high marks coming out of those. And then our last week of class, and this is the official last week in the schedule. That is May 10th and May 12th. May 12th is our last day of class, and that'll be the day we have our final exam. On May 10th, we'll have a review. So anything and everything from the beginning of the course to the end is game for the final. So that'll be covered on May 10th. May 12th, we'll have our final exam at the hangar. Same setup, just a longer exam. You can expect 9 to 10 problems on the exam, ranging in difficulty from the simple exam questions that we had at the beginning, just doing some basic math, up to and including truss analysis and the material we're doing in the last couple of weeks here with stress and strain and material science. So, and I'll post sample exams. Probably next week, I'll post an exam 3. Week after that, I'll post a final so you can see what to expect from there. So tonight we are taking a look at the basics of strength of materials. So we are leaving the world where we assume our materials have infinite properties and can never stretch or fail. and starting to look at what reality is. Tonight, we're going to look at normal stress and strain. We'll look at what we call shear stress and strain on Wednesday night. So first we have to define the concepts, define the basic idea and the context that stress and strain are used in. And we can best illustrate the idea by looking at a truss problem. The goal in solving a truss problem was to find out how the structure was handling the load that was imposed on it. So we apply some forces. There are some loads, maybe some weights, or maybe some side loads, some winds or something applied to this. And as a result, the different members carried a certain amount of load. Some were in tension, some were in compression. And that's where the truss problem stopped. We didn't go any further than just saying, okay, member AB carries 2.3 kips in tension. Well, if we actually had to go build this structure, we'd have to consider, well, we've got to handle 2.3 kips in tension. What material are we going to use for that? What should be the shape of that material? And how can we determine what will work and what won't? I think we have some basic ideas of what would work and what wouldn't. A small piece of threaded rod probably isn't going to do the job, but you probably don't need an I-beam that would span a highway or a river. Somewhere in between. How do we figure out what'll work? Or if we have a candidate part, how can we figure out if that part will handle the load? And that involves discussing stress and strain, because it's the external loads that are applied to a material, that external 2.3 kips, has to be handled internally by the material. And so a lot of our discussion here will focus on the external versus the internal. Externally applying a load versus the internal forces that are generated between the molecules and the bonds that make up the material. Stress is a way of discussing what's going on internally. And strain is the result of that, which we'll see here as we get a little further in. So we never really asked, when we built up a truss or did the analysis of a truss, whether or not that member could actually handle the loads that we imposed on it. And we didn't consider shape or material. Now we have to. So to examine the situation more carefully and develop a picture of what's going on in the real structure, we need to look at what happens at the material level. So if we zoom way in on the material to the point where we lose the size of it, we're looking at it so closely, all we can see are the bonds between the molecules that make up the structure, or at least the member. That'll allow us to evaluate at the material level whether the forces are too high or not. So here's the basic picture. Here's some truss member in tension. And it's in tension here because it's got forces pulling on both ends. It's in equilibrium as long as those two forces are the same. So if this is 2.3 kips, we'd have 2.3 kips on each end pulling this thing apart. So in this case, I've said 20 kips. So that means 20 kips on this end and 20 kips on that end. So over here, we'd have 20 kips, and over here, we've got 20 kips. That keeps it in equilibrium. Well, think method of sections. If I cut through this member, if I had some sort of magic laser or very high-powered laser, and I could cut right through this member, if I didn't change anything, these two parts would fly apart from each other. What method of sections let us do was cut through a member and then ask, how hard do I have to pull on what's left behind to keep the structure in equilibrium? Well, we can ask the same question here. If I slice through this member, how much force do I have to apply to the part on the left to keep it in equilibrium? And hopefully the answer is pretty straightforward. It's 20 kips. But if I've exposed some area here, that 20 kips has to be spread out over the area. So there's my free body diagram after I've sliced through the member. If I've sliced through this member, these little forces that are exerting on the surface have to add up in total to 20 kips in order to keep this thing in equilibrium. Otherwise, it's going to shoot off to one side or the other. But if this area is big enough and it's far enough away from the end of the beam, we can approximate that there is a uniform distribution of force. So that 20 kips is spread out uniformly. And when we have 20 kips spread out uniformly over an area, we can figure out how much of that 20 kips is spread out over each square inch. So that's what we look at when we're looking at stress. What we're looking at in stress is how the applied force, how that external force is spread out over the area, the cross-sectional area of the member. So if we cut that beam and we zoom in, the force looks like it's uniformly distributed. Now that's true as long as we're closer to the center of the member. If we're down here at the end where the load attaches, if we have a pin here or something like that, that's a very different stress situation. That's where we end up with things in stress concentrations and all of that. And we'll look at those a little bit later on after we get the basics down. But here we have far enough away from the end that we have essentially a uniform distribution. We have 20 kips spread out over, let's say, 10 square inches. Well, if we have 20 kips spread out over 10 square inches uniformly, then that means each square inch has 2 kips on it. We could say that there is a stress of 2 kips per square inch. Now, for those of you who are a little more familiar with fluids and working with fluid dynamics and what we do in hydraulics and things like that, you might recognize that unit. It's pressure. Essentially, stress is the internal pressure that a member feels when a load's applied to it. That pressure can be tension, pressure could be compression, but it's the load spread out over the area. Force spread out over an area is pressure. We just give it a special name when we're talking about structures. We call it stress. So stress is a pressure. It's a force spread out over an area. So since the force is uniformly distributed over the area, we can define that pressure. And because the letter P is used for other things, and we want a unique letter to distinguish stress, we use a Greek letter. And it's that funny looking thing here off to the left that looks sort of like a 9 fell over. It's the Greek letter sigma, which happens to be the letter S in Greek, essentially. It's the small letter sigma. Sigma is essentially the universal symbol, at least as far as this planet's concerned, to be the symbol for stress, for normal stress. And it's just simply the applied force divided by the cross-sectional area. So that's our stress. We call it normal because it's perpendicular to the surface. If we go back to this picture here, the stress is viewed as this distributed force. And because that distributed force is perpendicular to the area, we call it normal. Normal is a math way of saying perpendicular without using so many syllables. We save one, normal versus perpendicular. So, okay, we save a couple of them. But normal means perpendicular. So normal stress is at 90 degrees to the surface. And essentially, we consider it to be the material or the internal equivalent of force. It is generated when a force is applied externally. Essentially, it's the material's response to an external force. The internal response to an external force is stress. So it's how much force acts on a unit area. And when we find the stress, something kind of important happens. We actually lose the details of the shape of the member. So for example, here, let me go over to the board or to the page, and we'll see what this looks like. Let's say I have one beam here. I've got 20 kips on this end, and I've got this distributed force that has to add up to 20 kips, spread out over whatever the cross-sectional area is here. If I total this all up, it's got to add up to 20 kips to oppose the 20 kips on the other side. Now, if I were to draw a cross section, so we'll call it cross section A. If I do a cross section through this member, maybe it's a rectangular beam. So over here in my view AA, I could have a rectangular beam or a square beam. That would have a certain number of square inches to it. Maybe it's a piece of channel. Maybe it looks something like that. And that's section AA. Could be all sorts of different things. But what's interesting about stresses is that once we calculate this out, we have our normal stress is the force applied divided by the cross-sectional area. Once we figure out that cross-sectional area, let's say over here the area is 10 square inches. And let's say that with the sizes on there, this area is also 10 square inches. Now, these are very different shapes, but they could easily have the same area if the dimensions were correct and all of that. Our stress is whatever the force is, 20 kips, divided by whatever the area is, 10 square inches. Once we find out that our stress is 2 kips per square inch, it no longer matters whether this was this L channel or whether it was a rectangular or a square profile. We lose the details. It doesn't matter anymore what the shape is. In fact, we most often just need the shape so that we can calculate the area. Once we know the area and we divide it out, it doesn't matter what that shape was. We have 2 kips on every square inch. We've lost the external geometry, and essentially we're zoomed in so close that all we're looking at are the molecules that make up the structure. We've jumped into the internal structure of the member. So we've lost that detail of shape. And that's important because that means we can now apply it to anything. We could say, well, if I have this stress of 2 kips per square inch, maybe I could pick a different shape or apply that to a different situation. I know 2 kips per square inch is the stress that member is going to have to handle. It also makes it so that when we look at limits, and we'll be looking at material limits here at some point, the ultimate strength, how much stress a piece of material can handle or a member can handle, comes down to the stress. It doesn't come down to the force. The force depends on the details of the shape. The stress that this material will break at only depends on the material. So as long as I know this material is made out of 2024 T6 aluminum, I can go and look up what's the ultimate stress for 2024 T6 aluminum. It doesn't have an entry in the table for 2024 T6 square channel or 2024 T6 angle. I don't need any of that. And it's fortunate we don't, because otherwise we'd have to have these huge tables covering every possible product anyone could make. Once we know the stress, it no longer matters what the details of the shape is or what those details are. All that matters are what the material is. So that's a huge simplification. That makes life a lot easier. So we lose the details of the shape of the member and how that shape is loaded. All that matters is what the stress is. So the stress captures a lot of information and digests it down for us into one number that we can then use for a lot of purposes. So that's the basic idea here with stress. It makes it possible to just focus on the material rather than the specific details of any particular member. So that's the idea behind stress. Now, let's go back to the picture here. The amount of stress we get depends on 2 factors. It depends on the force. So if we apply a bigger load to this, the stress is going to go up. It also depends on the area. The smaller the area, the bigger the stress. Let's say we decide we want to shift over to this L channel, and we find out the L channel is only 2 square inches in area. Well, That'll mean our stress will no longer be involved at 10 square inches. Now we're taking that 20 kips and spreading it over 2 square inches. That's going to give us a bigger stress, 10 kips per square inch. The smaller the area, the bigger the stress. And this factors into design because if weight and cost didn't matter, we'd just use the biggest cross sections we could possibly find. Keep the stresses as low as possible. We'd never have problems with it. But the structure we'd build would be heavy and expensive, especially important with airplanes. We don't want things to be excessively heavy. So instead, we try to find the limits. We try to find out what's the smallest area that will do the job for me. I've got to support these 20 kips. What's the smallest area? And that involves loading the material up to limits that are fairly high. There are structural limits. There are stresses that will cause permanent changes in shape and eventual breakage of the materials involved. So we have to be aware of those limits. We don't want to underload because it makes a wasteful design, but we don't want to overload because it makes an unsafe design. And so a lot of what engineering is about balancing those two objectives. How do we figure out how do we use enough material so the structure will be safe, but not so much material that we're wasting material and we're paying a lot for that material and it's heavier than it needs to be. You can think of it kind of along the lines of what you did figuring out wires and what gauge wire to use. Sure, we could run 4/0 to everything, have quarter size, welding cables running to everything, and it'd work, but it would involve a lot of copper and it would cost a lot of money when all we need is an 18 gauge wire to do the job or a 12 gauge wire to do the job. So we have to balance the objectives of safety and of waste and cost. Now, another note before we go back to the notes. When we've dealt with pressures before, we had pounds per square inch. Well, we had a shorthand for pounds per square inch. We called it a PSI. Well, we have a shorthand for kips per square inch also. A kip is 1,000 pounds. So rather than writing PSI, we would write KSI. So 10 KSI is 10 kips per square inch. And these pressures, these stresses can get very high. We can even get up into the millions of pounds per square inch in heavily loaded structures, highly stressed structures. Millions of pounds per square inch would be abbreviated MSI. So we have PSI for pounds per square inch, KSI for kips per square inch, and MSI for millions of pounds per square inch. I suppose you could call it MIPS per square inch. So a little on the terminology there. Now, stress isn't the only concern. Think about a spring. If I grab hold of a spring, say a slinky or something like that, really weak spring, I grab hold of that and I apply a force to it, the spring responds. It changes in shape. Materials respond to stresses by changing shape. In fact, most materials out there, at least most materials we use in structures, tend to behave a little bit like a spring. When you apply a force to them, they extend or they contract. If you apply a force in tension, generally the material expands. When you apply a force in compression, it generally contracts. How much it contracts depends on how much force you're using and on the material and the shape and size of what you're working with. We picture change in shape, what we call elongation. How much longer some part becomes or how much shorter it becomes. That elongation is an external value. It's something we could measure. We could put a tape measure on a beam and say, well, this is a 1/4 inch longer than it was before we loaded it up. The internal equivalent is what we call strain. Internally, we can think of how much each inch of the material grows. So maybe each inch becomes an inch plus 5 thousandths. Now, how much the overall member grows is going to depend on how many inches are involved, how long that is. If each inch grows by 5 thousandths of an inch, you're going to need lots of inches put together before you'll be able to put a tape measure on that and actually measure it. But strain and stress are connected together. Stress is the internal equivalent of force. Strain is the internal equivalent of deformation, of change in length, of elongation. And stresses cause strains to occur, just like forces cause elongation to occur. So when we pull on a material, it stretches. That's elongation. When materials are pushed, they tend to shrink. There's a name for this in materials. We call it Hooke's law, because most materials, at least as long as we don't push or pull them too hard, or we don't exceed certain limits, there's a nice proportional relationship between force and elongation. We call that Hooke's law. Hooke's law says that for every pound of force that I apply to a spring, I'm going to get a certain number of inches or a certain fraction of an inch of length change. And that's a nice simple proportionality. So we can tell pretty easily if I put 10 pounds of force on it, how much elongation I'm going to get. I'm going to get 10 times more than what I get out of 1 pound. It's a nice simple proportionality. This nice simple proportionality fails when we put too much load on things. There is a limit to how much force we can put on something to have it obey Hooke's law, and that's a limit we're going to have to become familiar with as we get into practice on this. But Hooke's law is a law of proportionality. It says the harder you push something, the more length change you get. In a sense, if you're more familiar with electricity, you could think of Ohm's law. Essentially, is a rough equivalent of Hooke's law. Voltage is pressure, current is essentially change in motion, it's change in shape. So you push harder, you get more flow. You push less hard, you don't get as much flow. And the proportionality is all about the material, it's the resistance. So there's a lot of laws of nature that we have behave like this because we like looking at things that behave this way. We like to see nature as behaving proportionally because proportional things make sense. Proportional things are easy to work with. And when nature doesn't do that, we design it so that it's proportional. We try to control it so it's proportional. So we're really attached, our human brains can only really handle proportionality. And we purposely design systems to respond proportionally because they make the most sense to us. So here's the picture with strain. On the top, I've got some beam or some member that has a length L when it is unstressed. So with no load applied to it whatsoever, it has a length L. Sometimes we call this, and when we talk about springs, we call it the rest length of a spring. This could be a structural member. Maybe it's 10 feet long when it is unstressed. In the bottom picture, we've applied a load to it. And as a result of that load, the length increases to some new value. And it increases by the amount that's shown over here. This funny looking character over here is another Greek letter. It's the Greek letter delta. It's a small delta. You may be familiar with the capital delta as the triangle, but the small delta is what we're using here. Delta represents a change. In this case, it's a change in length. It's how much this member has expanded. We refer to it as the elongation of the member. If the elongation is positive, then it means it's stretched. If it's negative, it means it's shrunk. So that's the elongation. So when a member stretches, its length increases beyond its unloaded length by some amount that we call delta. So the original length is L and the deformed length is delta. We define the strain to be that elongation delta spread out over the entire length of the beam. So, in a sense, even though we could slap a tape measure on this and say, well, this, let's say, 100-inch beam is now 10 inches longer. What we imagine with strain is how much each little piece of the member, how much did each of those 100 inches have to grow so that in total we'd have 110 inches of length. Rather than thinking of just the very end of the beam extending by 10 inches, we look at how that extension is spread out over the entire length. That's the definition of strain. So in strain, we look at the elongation delta, the 10 inches in my previous example, and we spread it out over the rest length, the 100 inches. That gives us the strain. The strain is the elongation divided by the original length. So after you work out the changes, it's just delta over L. And the symbol we give to that is this other little kind of funny looking character. That character we call epsilon. It's a Greek letter, and it's used fairly frequently in mathematics to represent a small quantity. Epsilon refers to a small amount, and strain is usually a small number. So let's take a look at a couple examples of strain. So strain is all about length and deformation. It doesn't actually matter directly, it doesn't calculate directly from force or from stress. Stress doesn't really factor in here. We're going to see in a moment that there's a connection between stress and strain, and there's a proportionality there. The more stress you have, the more strain you get. But as far as calculating it goes, you don't have to do anything but length measurements to calculate strain. So let's take a look at that here. So let's take a member that at rest is 100 inches long. And when we apply some load to it, so some amount of load in tension, I don't know how much, but some amount of load in tension makes this go to 110 inches. Our value for delta is the deformed length, 110 inches, minus the rest length. It's where we started minus where we ended up minus where we started. So it's the elongation. It's how much it grew. And it grew by 10 inches. That's a real physical value. That's something we can measure. To define the strain, we ask, how much did each inch grow? We had an elongation delta, some amount of extension in length. We're going to spread that out over the rest length of the member. So for our example here, we have an elongation of 10 inches. We have a rest length of 100 inches. Now the number here would be 0.1, 1/10. And the units are kind of interesting. If you look at the units, it's inches per inch, or they just cancel out. Now, some people like to just cancel those out and say we had a strain of 0.1. And that means each inch grew by 0.1 inches. I like to kind of leave it in and just say it's inches per inch, which means that each inch grew by 0.1 inches. It's a 0.1 inch per inch. Now, the advantage of canceling out the units is you could then apply it to anything. You could say, well, what if I had the same amount of strain in a 10-foot beam? Well, each foot would grow by 1/10 of a foot. So I would have 10 feet times 0.1, I'd have 11 feet by the time I was done. When you drop out the units, you can then insert whatever units you want. So feet per feet, mile per mile, meter per meter, it doesn't make any difference. It's the same amount of strain. But since we tend to stick in the materials, in the standard world, inches work perfectly well for that. So the strain here of 0.1 means that each inch grew by 0.1 inches, and that's a lot of strain. It'd be more realistic to say that this 100-inch member grew by 1 inch. Well, if it grew by 1 inch instead of 10 inches, if we only had 1 inch, then we only have 0.01 or 10 thousandths of an inch per inch. And typically that's around the neighborhood. That's even kind of big for most structural materials to have 100th of an inch per inch. Generally, we're looking at thousandths of an inch or less. A lot of times it's hundreds of micro inches or tens of micro inches. So generally very, very small until we start getting up to up to really, really large forces or really, really small cross-sectional members where the stresses are pretty high. But generally you can expect the strains to be very, very small. Thousandths of an inch or less is common. So that's the definition of strain. So we've got stress and we've got strain. Stress is created by force when force is applied. The material responds by straining. Strain is deformation. It's what happens at the molecular level to add up to the overall change in length of the member. Now, so strain is a measure of relative deformation. It's deformation compared to the overall length. So it tells you how much each unit length has increased or decreased in size. If the stress is positive, then the strain is positive, it increases in size. If it's negative, it decreases in size. So I like to think of the strain as the amount of stretch or shrink, the amount of deformation spread out over the length of that member. That's where the division comes in. And this is a material quantity. Once we divide out that length and we have 10 thousandths of an inch per inch of growth, we don't need to know how many inches we're dealing with anymore. We could then apply that to something longer and say, well, if I'm dealing with a 10-foot long piece, a 120 inch long piece, how long is that going to grow to? We can apply it to a different situation because we've internalized, we've gone inside the structure and we've lost the external geometry. And that makes comparison pretty easy. We can say, well, for 2024 T6, the strain was 0.01 inches per inch, but for titanium, it was 0.001 inches per inch. So we can compare between materials a lot more easily as well. And that's useful for design. Now, stress and strain do not happen independently of each other. Stress causes strain, or stress induces strain. Just like in the external picture, force caused elongation. Force caused a material to stretch. Stress and strain are related to each other, and there's a Hooke's law, essentially, for stress and strain, a way to tie together stress and strain. And since stress and strain only depend on material, the relationship between stress and strain only depends on the material. There is a constant of proportionality in Hooke's law for the external picture from force and length. We just call it a spring constant. We call it K. For stress and strain, the relationship between stress and strain is what we call Young's modulus, or the modulus of elasticity. Some fancy words there. Modulus refers to how something is changing. And the modulus of elasticity, we usually use the letter E to represent that, the capital letter E. And we can write down Hooke's law for stress and strain like that. Stress equals Young's modulus times the strain. Now, based on what we've already looked at so far, stresses tend to be big numbers. Thousands of KSI, millions of KSI. Strain tends to be a small number, 0.001 or smaller. That means that if we're multiplying a small number and getting a really big number, the modulus of elasticity must be huge. And typically, this is where we see MSI coming in, millions of pounds per square inch. E is a very large value. E can sometimes be thought of as the stiffness of the material, because if we turn this equation around, and I'll go over to the page on this one, if we turn the equation around, stress is equal to Young's modulus times the strain. If we turn it around and solve for the strain, we'd have stress divided by Young's modulus. Well, stress is a pretty big number. Strain is tiny. So E must be really, really huge. Young's modulus must be really huge to get small amounts of strain. Now, if we have a really stretchy material, a spring, something that's going to expand a lot, then that means we can put some stress on it and we'll get lots of strain. The Young's modulus for those materials tends to be fairly small. Things like rubber, for example, would tend to stretch out a lot. Elastic materials, they're not very stiff. So when Young's modulus is small, we have an elastic material, we have a stretchy material. When Young's modulus is big, that refers to a stiff material. The stiffer a spring is, the harder it is to get it to change shape based on the load. You have to push harder or pull harder to get it to change shape more. Stiff materials don't strain very much, even under a large amount of stress. So it's stress that induces strain, but stress gets cut down by Young's modulus. So if Young's modulus is very big, like it is for a lot of structural materials, we're not going to expect a strain until we put a lot of stress on it. So those are the three values that are tied together here: stress, strain, and Young's modulus. There's a proportionality. We push harder, we get more strain. We don't push as hard, we get less strain. Just like when we had F equals K times L, that's Hooke's law. Force equals some constant times the length. So there's a proportionality there. This side's all about what's going on inside the material. Young's modulus we can look up in a table based on what material it is. There's one value for 2024 T6. There's one for 6061 T3. There's one for 7075. There are different values if the material's annealed versus heat treated. There's different values for titanium. We don't have to worry about the shape or size. All we have to worry about is what the material is, and we can look up that value. So that's a big advantage in dealing with the material view of things. So that's Young's modulus. So Young's modulus is usually a big number, basically millions. 1 to 10 million is common for typical materials. It's not uncommon at all to have 20 million pounds per square inch be Young's modulus. So it takes a lot of stress for most materials to get even a little bit of strain. Most materials we use in structures tend to be stiff. So normal stresses are what we find in a material. When we exert a force on a load on a member, those stresses act perpendicular to the surface, and we get a normal stress, the force spread out over the area. And that's where my note is that normal is just a mathematical term for perpendicular that we use when surfaces are involved. Any questions so far?
Nope.
So the last slide here before we do some examples, the last slide here kind of sums everything up, and I like to think of this, I've never really seen this anywhere else, so this is as far as I know, my creation. Maybe somebody's maybe I saw it somewhere and I copied it long ago, I don't remember, but I've never really seen it anywhere else in any other books. But I call it the material loop, where we start out with the factors that affect how a structural member reacts to a load. If you think about what's going to happen when we load this thing up, we build this bridge, we put some loads on it. How are the members going to respond? And what's going to matter? Well, the first thing that's going to matter is the load, how much load we apply. And that, hopefully, it's pretty obvious why that would matter. There's a limit somewhere. And somewhere there's a limit between the structure surviving and the structure breaking. And so the load we apply definitely matters and is definitely going to control how the member responds, because it's the difference. It could be the difference between breaking and not breaking. Geometry is important. Size and shape, how long it is, and what the cross-sectional area is. Those are the two factors that matter the most. And this is real design stuff. I just designed a structure for to support a 2,000-pound fish tank. And I want to make sure when we fill this thing up, I'm not going to end up with 2,000 pounds of water all over my floor, and rock and all that stuff. So, and all I really needed in order to do that design was what geometry I was working with, what loads I expected, and our third factor that I'll list here in a moment. But length and cross section is all that really comes into play. It's all we need to know. And there are big tables published for commonly available structural materials. I was working with square tubing, and they tell you things like the cross-sectional area, the thickness, the length you can get in. All of that is easily available. It's just geometry. The last factor is what the material is. Is this structural steel? Is it aluminum? Is it wood? Now I'm working with ASTM A500 or A500 structural tubing, and A500 is a common structural material. We can look up things like Young's modulus and the spring constant for that. Those are things that are easily available. People have tabulated them for over 100 years. These things have been tabulated out there. So all these materials have different properties, and they enter the whole setup through these constants, through Young's modulus and through the spring constant. If you look up what that is, well, we can put all these together and we can relate them in this loop or this chain, and it's essentially describing how the material ends up responding. From the outside picture, we're interested in length change. I want to know, if I load this member up, is it going to stretch out too much? How much is it going to stretch out? That's the response to the load. Materials don't generally stretch out on their own. We have to apply a load to them. So when we apply a load, how much is it going to stretch out? And we can work through the material to figure that out. And that's important if we're doing design, because we want to know the material properties. So here's how the loop works. And this is, if you see this slide in the notes, if you've printed them out, you're probably just going to get one picture. This is all animated in my setup. So I'd flag the time on the video, so you can go back to it and watch how these all get put together to make sense of how these values interact. So we've got our two pictures. We've got the external and the internal picture or view of the material, of the load, or of the member that we're working with. And we start out with our applied force. This might be, if we're just dealing with a single structural member, it might be the actual applied load. It could be what we figured out from a truss analysis that said this member's carrying 20 kips in tension. That's our force that's applied to that member. Force applied on the outside, on the external side, generates a stress inside. And that stress is symbolized by the letter sigma. That is our normal stress. These two are connected by area. So to get to the stress from the force, we need a piece of geometry. We need the area. The normal stress was the force divided by the area. Well, once we know the stress, we know a lot about what's going on. We can go to a table and say, well, I want to try and put 20 kips on this member. It's got a 10 square inch area, so 2 kips per square inch. And I want to make it out of 2024 T6. So I go to my table and I find out, well, what's the maximum amount of stress that 2024 T6 can handle? And if 2 kips per square inch, 2 KSI is below that, I'm good. That's always a very important check to make. You don't want to work your way through all the design and then find out, well, this member can only handle 1.5 kips of stress. If I've got 2, this thing's going to fall apart as soon as I load it. I'm not going to be worried about how long of a stretch I'm going to get out of it. I'm going to be worried about the thing staying together. So we always want to do a sanity check. We're not going to talk about material limits tonight. We're going to look at that on Wednesday night. But we always want to stop and compare our stresses to the limits for the material to make sure we're not breaking things. This kind of thing, unfortunately, happens from time to time. There are lots of case studies out there of situations where people thought they had a design right, but they missed a step somewhere and didn't realize they were overloading the structure. And unfortunately, they didn't realize that until it failed. In some cases, it was just expensive cleanup. In other cases, it cost people lives, or at least injury as well. If you drive on Route 5S around here, going, or not Route 5S, excuse me, Route 49, going by I think it's Whitesboro High School. There's a bridge. There's a footbridge. It's meant for pedestrian traffic going over that highway. Well, that bridge was built back in around 2003, 2004, when they were redoing that whole highway. There used to be another road that people would go on, River Road. People would go on that road to get to Rome, and it would be slow. You couldn't really get onto 49 until a little bit later. So this little bypass was created, and they were working on that, and they put this interchange, or they put this bridge, this footbridge. The designer, that bridge that's there now, it's a blue bridge, and that bridge that's there is actually the second bridge to be in that position, because the first one collapsed during construction. The way it happened was the person who designed it with the weight of concrete in the bridge. They were going to use concrete over the footing over the bridge to act as the bed, and they had calculated what the weight of the concrete was, and they designed the structure to make sure it would handle the weight of that concrete. And unfortunately, it missed everyone who did a review on that design and signed it off before. And dozens of people look at these things before it gets signed off, and they actually build it. No one saw that the weight of concrete they had included was the weight of dry concrete and not the weight of the concrete wet. If you know anything about concrete, you know you end up adding a lot of water to concrete when you pour it, and then that has to dry out in order to cure, and it loses a fair bit of weight in doing that. It loses the water through evaporation and other processes. Well, as they were pouring the concrete into the bridge structure, it was overloaded and the bridge collapsed. You might occasionally see on the eastbound side of that bridge, you might occasionally see a cross there, because somebody did jump from the bridge and was injured, and I believe he later died as a result of his injuries that happened as a result of that. So you'll see a cross in the ground there every once in a while. Someone goes through and marks that position. But these kinds of things, these ideas of stresses, can have really big consequences, and if we don't check very carefully to make sure that at no point we are overloading that material, then we're setting ourselves up for disaster. So that internal stress check is important. Once we've passed that internal stress check, we want to know what our strain looks like. How much is this thing going to change shape? We're convinced it's not going to fall apart. We know it's not going to stretch to the point where it fails because it's within its material limits. But we want to know how much length is going to change. That matters, because if you think about it in a truss, you used a lot of the geometry, the lengths of those members and the positions where the joints were. That all factored into your analysis. Well, strain here is going to tell us about that deformation. And if that deformation is too much, it's going to change what we think the stresses are. and it's going to change what the loads are because the geometry of the structure is going to change. Well, to get to strain from stress, we need something about the material. We need to know something about what that material is, and that's where Young's modulus comes in. Young's modulus is a different value for each material. It's the stiffness of the material, and it tells us how much each inch of that material will grow when we apply stress to it. So we apply a stress, we get a strain, and the moderating factor, the proportionality, is the Young's modulus. So that's where we get a material input. We only had geometry up to the point of calculating the stress. We only had geometry. Young's modulus is about material. Checking the limits on stress is also about material, but that's not reflected on the loop here. And then finally, we want elongation. We want deformation. We want to know how many inches is this thing going to grow by when we apply our load. So strain can tell us that. Strain tells us how much each inch grows. If I want to know how much the whole structure grows, I'd have to multiply by the number of inches. That's the length. Another factor of geometry connects the internal view to the external. The internal strain, how much essentially the bonds inside the material grow versus what that all adds up to on the outside. That's our elongation. And as it's illustrated so far, this is basically how we do calculations. We have an applied force, and we know we're using a 2-inch by 2-inch beam. So we can figure out the area. That gives us our stress. We can look up what the material is that we're using, and that'll give us the Young's modulus, and we can use Hooke's law to figure out the strain. And then we know something about the length. It's 3 feet long, 36 inches long, so we can then calculate what our elongation is. And that path is usually the easiest and safest one to go through. We can kind of get back. We can complete the loop or close the loop. There is a connection between elongation and force, and that's the spring constant. That's the external view of Hooke's law. So Hooke's law over here is the connection between applying a force to something and seeing how much it stretches. In the internal view, it's applying a stress to something and seeing how much it strains. Now, I've added in two other things here. Shaded that right there. The vertical here is what is connecting the external and the internal views together. That's geometry. It's all about area and length, cross-sectional area and overall length. The horizontal, connecting the influence to the response, essentially the force to the stretch or the stress to the strain, that's all about material. Spring constant depends on material and material alone. Elongate or the Young's modulus depends only on the material. So the connection between the load and the response of the member, that's all about material. The connection between the external picture and the internal picture, between force and stress and elongation and strain, that's all geometry. That's how those two factors of material and geometry influence how that structural member is going to behave when loaded. So that loop can help you kind of figure out various problems. We can use it in lots of different ways. When we use it for design, we sometimes bring in what the material is and what we expect the stresses to be, and we try to figure out, well, how small can we make the member so that it maxes out the stress, or it gives us some small amount below the maximum stress so we can be as efficient as possible. So we mess with the order a lot to try to figure out what's going to work best. But in principle, if we know what we're working with, we know the load, we know the geometry of the member, we know its area and length, and we know the material it's made out of, we can figure out how long it's going to stretch, how much stretch we're going to have, and whether it's going to be safe. So that's the basic idea here behind stress and strain and the fundamental principles. Now I want to go through just basically one example on the record here, and then I'll pause and work a couple other examples after our break. So let's try an example here. Let's say we've got a member that has 15 kips on it in tension. That member is going to have a length of, say, 60 inches. And the cross-sectional area, if I draw a little cross-section here, we'll make cross-section AA here. We'll make it kind of a plate. We'll have, let's say, 2 inches that way by 1.5 inches that way. So that's our section AA. There we are. So that's what our cross-section looks like. So let's take a trip around the loop and see if we can figure out how much extension we're going to get here. So the first thing we need to know is how to get from force to stress. And we only have essentially 3 equations that we need to work with for any of these problems. It's just modifications of 3 equations. We have the definition of normal stress. That's force divided by area. We have the definition, the connection between stress and strain. That stress is equal to Young's modulus times the strain. And then we have the definition of strain. Strain is elongation or deformation, delta, divided by the rest length, L. Those are the 3 big equations to keep handy when working in any of these kinds of problems. The order may change. What information we have versus what information we want may change, but those are the 3 equations that we're going to be working with. So let's try it out here. Let's start with our force. Well, our force is 15 kips. That first chain in the loop was to figure out stress. So stress is force divided by area. I've got a force here of 15 kips. And I've got an area, according to my drawing here, of 2 inches by 1.5 inches. So one of the things you're going to have to remember in this section is how to calculate areas. And sometimes these are simple areas, just a simple rectangle. Maybe sometimes there'll be stuff removed from the inside, or it could be built up out of different materials, or different shapes. So you have to know how to calculate areas. So I'd assume you'd know how to do that. I'm not going to give you equations typically for calculating areas. So you should know how to handle an area of a circle, area of a square, things like that. Well, the area here, rectangle, length times width. 2 times 1.5, that's 3 square inches. So my stress is 15 divided by 3, it's 5. And my units are kips per square inch, or KSI. So I've got a normal stress of 5 KSI. That's what's going on inside the material. Each square inch of cross-section is holding on to 5,000 kips. 5 KSI. Now to go any further, I've got to pick a material. So I'm going to go to my reference book here and see if I can find a material. And I think we'll use, let's say we've got, we can use A501 steel. So A501 steel is a structural steel commonly available. It's basically what you go and get down at the local supply house to build anything that you might want to weld together, something like that. First thing I'm going to look up here in my table is what we call the ultimate strength. Now, this is a check. This is not something we have an equation for. This is about the limits of the material. And we're going to define officially next time ultimate strength. But ultimate strength you can think of as basically the maximum amount of load that a material can handle. Well, in this table, for A501 steel, my ultimate strength is 58 KSI. Well, I'm only loading this up to 5 KSI. So this is going to be safe. It may not be efficient, but it's safe. It's not going to come apart. So 5 KSI, so I'm definitely below my ultimate strength, so I can proceed. If I'm not below my ultimate strength, the problem stops here because we know it's not gonna pass. And in fact, there's really nothing in the table with a with an ultimate strength below 5 kips. About the lowest it gets in this table is cast iron. Cast iron has an ultimate strength of 20 KSI. So if this was a cast iron beam, I might be loading it up a little bit much, but I'd at least be it would be over it would be more than 58 KSI. So that's our ultimate strength. So I know it's going to be safe there. So we can proceed. So let's take a look at the strain. Well, stress and strain are related through Young's modulus, and Young's modulus depends on the material. So I need to know Young's modulus first. And according to my table, Young's modulus in KSI is 30,000. So 30,000 KSI, that's a pretty big number. That's 30 MSI. Now, it has the same units as stress because strain essentially has no dimension to it. Strain is just inches per inch. So the units cancel out. So since this is just a number, whatever unit we want over here has to also be carried by the Young's modulus, since we're just multiplying by a dimensionless number. So Young's modulus has units of stress. Essentially, you can think of Young's modulus as the amount of stress you'd need to get each inch to grow by 1 inch, if that was physically possible. Now, you'd need more stress than the ultimate stress to get that to happen, but that's one way to capture how large the Young's modulus is, that to get strain to be 1 inch per inch, so each inch grows by another inch, it doubles in size, you would need Young's modulus as your stress. That's way, way above any ultimate stress. So these are really, really large values. And so we could expect in normal use very, very small strains. Now, to figure things out here, we would turn this around to we'd turn Young's modulus, the Hooke's law around by dividing both sides by the Young's modulus. So we'd say our strain, since that's what we want to get, is stress divided by Young's modulus. And frankly, that's a better way to write it anyway. They only write it out on one line because it's easier to print that way. It's closer to the definition. It would be like taking the stress equation here and saying force equals stress times area. It's not as informative as a way to write it. So I'd probably write Hooke's law kind of like this. What I get, the strain, is stress divided by Young's modulus. So we've got a stress of 5 KSI, and we've got a Young's modulus of 30,000 KSI. Very important to note the units here. The units have got to be the same in the top and the bottom. If they are different, then the math isn't going to be right. It's not going to work out. You're going to be usually a factor of 1,000 off one way or another. Some resources give you the Young's modulus in MSI. So if you plug in 30 and you just take 5 divided by 30, you're going to get a much bigger strain than what you really should have. You'll have 1,000 times bigger because you didn't match up the units ahead of time. If the good rule of thumb to follow is if the loads are in kips, everything should be in KSI. That way you keep everything straight. You avoid these factors of 1,000 that you might be off by. So we can divide this out. So so we can go and calculate it out. So we go over to the calculator. We've got 5 divided by 30,000. That is 0.000167. And that is the strain. Now we can interpret strain as being inches per inch. So what that tells us is each inch grows by 167 millionths of an inch. So that's not very much at all. So 167 millionths of an inch per inch. So that's the second link in the chain, going from stress to strain through Young's modulus and the material. Now we can go back to jump into the physical picture because we want to find out what the actual physical length change is. That comes from our definition of strain. So in fact, it actually makes more sense to multiply this one out, cross multiply it and write it delta. The elongation is the strain, which tells us how much each inch grows, times the length, how many inches we've got. So we have 0.000167 inches per inch times 60 inches. So if we multiply that out, we get 0.01 inches. We get 10 thousandths of an inch, or a hundredth of an inch. So overall, this 60-inch long member will grow by 0.01 inches. If we put a 15,000 pound load on it and it's made out of A501 steel. So that's a pretty reasonable calculation. In fact, this would be to within 1,000th of an inch would be accurate. This would be what we actually get if we measured it. So we've got a pretty good handle on it from that kind of view. We can reasonably accurately predict the behavior of these materials down to pretty high resolutions. So that gives us our elongation. Make sense there?
Yep.
So pretty straightforward. There's really not a lot to it. Once you get the basic equations down and what they mean and get some of the terminology down, stress, strain, elongation, length, force, area, it's really pretty straightforward. All right. Any other questions?
Nope.
All right. Well, we'll pause for break. And we're back. So let's take a look at one more example. I want to do a compression example here. So let's set up a member. We'll go with 5 kips in compression. And let's see, we'll make this 36 inches long, and we'll give it a cross section of, let's do a little I-beam. So something that looks sort of like this. And the good thing about things like I-beams is they come in standard sizes. So if this is, I can look up a standard sized I-beam, which for reasons that are somewhat lost to history, I suppose. They're normally referred to by W profiles. If I pull up one of those, let's see here. There we are. So properties of I-beams. Let's do a W 18 by 40. So all this does is show the cross section, W 18 by 40. And what those numbers mean, we'll get into a little bit later. But all that really matters for our purposes right here is that the area for a W18 by 40 beam, the area is 11.8 square inches. So for complex shapes, as long as they fall into standard properties, we have information we can look up in references. So with a compressive load, we can use signs to help us out here. So first we want to find, our end goal here is to find how much is this going to compress by. So we want to find what would otherwise be called the elongation, but here it's going to be a smaller number. It's negative. So it'll be the compression, I suppose, or the delongation. It'll be something shorter. So we want to find our elongation delta. We're going to do it by first finding the stress, and then from the stress finding the strain, and then from the strain we'll find the elongation. And it helps if we model in our equations a compressive stress as negative and a tensile stress as positive. That'll get the signs right so that compression reduction in length will come out negative, while an increase in length will come out positive. So we'll say here that our force is -5 kips. So first we'll find our normal stress. Normal stress is force over area. We have a force of -5 kips spread out over an area of 11.8 square inches. So we have 11.8 square inches. We divide -5 by 11.8. And that gives us 0.4237 KSI. So -0.4237 KSI. So that's the stress. Now that's a pretty low amount of stress. And in fact, it wouldn't even really be a concern to look up whether this is anywhere near the limits, because we don't even have a limit on compression. Materials don't tend to fail in compression in the same way they do in tension. In tension, they tend to eventually form a crack that weakens the structure and causes it to fall apart. In compression, the main factor that affects failure is not the stress, but the relationship between the cross-sectional area and the length. So something here that's 3 feet long, but has this W18 by 40 profile, that is going to fail in a mode that we call buckling, where the middle will kick out in one direction or another as a result of the stress. Now, buckling's a little bit beyond the scope of this course, so for our purposes here, we're going to assume that that we're beneath any of the limits that might apply to buckling. So we don't have to worry about this buckling. If it was a concern, we could reduce the length or we could make the profile thicker. Both of those increase resistance to buckling. But here we'll assume this is not going to buckle. So we've got a stress of 0.4237 KSI in compression. So each square inch feels 423.7 pounds, squeezing it together. So for our strain, we'll get our strain from our stress divided by the Young's modulus, and we'll stay with our A501 steel. So we'll stay with the 30,000 KSI. Well, excuse me, 0.4237 KSI divided by 30,000 KSI. So that divides out to be a fairly small number. Bunch of zeros. 1412. So keeping 4 sig figs here. And that's inches per inch, or dimensionless. So each inch is only going to shrink, don't forget the sign here, negative. So each inch is going to shrink by about 14 millionths of an inch. So unless we have an awful lot of inches to work with, this is not going to be a very measurable contraction. Elongation is the strain times the length. The strain tells us how much each inch changes. The length tells us how many inches we're dealing with. So we get negative 0.00001412 times 36 inches. Now be careful here when you are, if you're using feet, you might have to do some conversions. It depends on where you're using the feet. We'll get into some more complex problems with that next time. But if we multiply that by our 36 inches, then we get negative 0.00051 inches. So this thing shrinks, this 36-inch long I-beam will shrink by a little bit more than half a thousandth of an inch. So it's a 510 millionths of an inch. So very small amount of change. The steel is pretty stiff, and we really weren't loading it all that much. So we'd expect a very small change in size. I mean, that's on the order of thermal expansion. In fact, I wouldn't be surprised if thermal expansion and contraction were bigger than the stress-driven contraction. All right, so that's another example using those basic equations. Next time, we will be taking a look at material limits. We'll look at tensile testing and how that's done, and what the critical limits are when we load a structure in tension. We'll also be taking a look at shear stresses, and shear stresses are particularly important to us in aviation, since shear stresses are what rivets are designed to handle. So we'll work on a little bit of some rivet problems, see how those work out. Have a good night. I will see you on Wednesday.